In section 4.1, we are solving systems of linear equations by graphing. Our objectives are to determine if an ordered pair is a solution of a system of equations in two variables, solve a system of linear equations by graphing, and without graphing, determine the number of solutions of a system. We have three cases when we're solving systems of linear equations. Each equation is a linear equation, so the graph is a line. When you're graphing a system, which is two linear equations, we're graphing two lines. Those two lines could intersect at one point, and that point is called the solution. So we see our case 1. Whatever the coordinates of that intersection point is the solution to the system of equations. That means if you evaluate both of those equations, given the coordinates, both of those equations would be true. The other case we have is that it is possible that there's no solution. When you graph the two linear equations, you're graphing two lines. And in some cases, you will see that the lines will be parallel. So we have no solution. There's never going to be an intersection point. So we say that that is an inconsistent system of equations. And our third case is that we may have infinitely many solutions, that when you graph both of those lines, they end up being identical lines, and all of the points of intersection are the infinite number of points that appear on that line. So there's infinitely many solutions, and we call that kind of system dependent. In the graphing method, we follow these three steps. We carefully graph both equations on the same set of axes, we find the intersection point, and we check the solution in both equations. Here we want to determine whether the ordered pair is a solution of the system of linear equations. In the first examples, we're given a point, and we're given the system of linear equations. For our first example, the point given is -4, -5, meaning x is equal to -4 and y is equal to -5. What we want to do is test that to see if those values result in true equations for the first equation and the second equation. If they are solutions to both of those equations, then we say it's a solution to the system of linear equations. Let's begin with the first equation. X plus y is equal to -9. If we plug in x equals -4 and y equals -5, does that equal -9? Since this is a true equation, it is a solution to the first linear equation. We also need to check the second linear equation. The second equation being x minus y equals 1. Again, we're checking when x is -4 minus when y is -5, does that equal 1? When we simplify this equation, we know that minus a negative, we can change that to a positive, and a -4 plus 5 does equal 1, so we know that that is also true. So that means -4, -5 is a solution to the system of linear equations. Now that also means that if you were to graph both of those linear equations on the same graph paper, those two lines would intersect at the coordinates -4, -5. Let's check part B. In part B, our given point is -5, -3. So x is equal to -5 and y is equal to -3. In order for that to be a solution to the system of equations, both of the equations must be true. So let's begin with the first equation, 2x plus y, does that equal -7 when we plug in the given values? Does 2 times -5 plus -3 result in -7? And 2 times -5 is -10, and -10 plus -3, that unfortunately does not equal -7. So we say that this is false. It is not a solution to the system of linear equations because that particular point is not true when we substitute. So it's not necessary to check the second equation because we already know that it's not a solution to the first equation, so it cannot be a solution to the system of equations. So we say -5, -3 is not a solution. For these examples, we will be doing graphing to find the solution. We want to solve each system of linear equations by graphing, and note that all systems in these examples do have a solution. We can graph in several ways. You can graph using the intercept method, or you can write each equation in the form of y equals mx plus b, where m is equal to the slope and b is equal to the y-intercept. The first equation can be solved for y by writing the original equation and subtracting 4x from both sides of the equation. When you do that, the result is y equals -4x minus 4. So we know for that equation the slope is equal to -4 and the y-intercept is -4. We begin graphing this line, going 4 units negative in the y direction, and then our slope is -4 over 1. So we can, from this point, we can move down 1, 2, 3, 4 units over 1, but we're off the page. We can also go in the opposite direction, up 4 units and then to the left 1, up 4 units and then to the left 1, and so on. We can connect those points with a line. Now let's graph the second equation. Again, we want to write that second equation in the form of y equals mx plus b. Our second equation is 5x plus 2y equals -2. We want to subtract 5x from both sides of the equation. When doing that, we get 2y equals -5x minus 2. And then we're going to divide both sides of the equation by 2 to get y equals -5 over 2x minus 1. In this example, let's graph the second equation. Okay, the second equation, 5x plus 2y equals -2. We're going to solve this for y by subtracting 5x from both sides. And then we divide both sides by 2 to get the equation in the form of y equals -5x, 5 over 2x minus 1. So our slope is -5/2 and our b is -1. We begin graphing the y-intercept where b is equal to -1. That's moving down from the origin 1 unit. And then we use a slope of -5 over 2. That's from that y-intercept, moving down 5 units and over to the right 2. And then we can also go in that opposite direction where we go up 5 units and over 2. And we can connect those points with a line. We can see that there is an intersection point where the two lines cross, and that is our solution to the system of linear equations. And the coordinates of that system, or coordinates of that intersection point, is -2, 4. And then our next step is to check the work. We want to check the solution -2, 4 by plugging it back into the original equations, both of them. We're going to replace the x in the first equation, so we get 4 times -2 plus y, where y is equal to 4. And we want to check to see if that equals -4. And that does, so we know that that is a solution to the first equation, but we also need to check to make sure it's a solution to the second equation. We're going to be replacing the x and the y in the second equation to get 5 times -2 plus 2 times 4. And by simplifying that, we do see that that equals -2. So that means we know that this is a solution to the system of equations. Let's try part B. Solve the solution by graphing. we're going to take our first equation, 3x plus 2y equals 11, and we're going to, equals 22. And we're going to solve this by subtracting 2x. We're going to write it in the form of y equals mx plus b. And when we simplify that, we get negative 3x plus 22. And by dividing by 2 on both sides, we get y equals negative 3/2 x plus 11. Now, unfortunately, that goes off my scale here if we use a scale of 1. So let's use a scale of 2. If we go by 2's, this would be 2, 4, 6, 8, 10. And we should go in the same scale in all directions, 2, 4, 6, 8, 10. So each of those blocks represent 2 units in the x and the y direction. So we want to make that adjustment so we can take the time and clearly see our graph. If you have a larger piece of graph paper, you can still use a unit of 1. Now when we do that, we're going to plot our y-intercept. We know that the slope is negative 3/2 and the y-intercept b is equal to positive 11. So we're beginning right here at positive 11 on the y-axis. From there, we're going to move down 1, 2, 3 units, and then to the right 2 units. 1, 2, 3 units, to the right 2 units, and so on. And you're going to plot enough points to get a nice line that goes through 1, 2, 3 up, 2 to the left. Okay, for our second equation, we begin with 2x plus 4y equals 28. We're going to subtract 2x from both sides. We want to get it in the form of y equals mx plus b. So we get 4y equals negative 2x plus 28. Then we divide by 4 on both sides, and we get y equals negative 2 over 4 can be simplified to negative 1/2 x, and 28 divided by 4 is 7. So for this one, our y-intercept is 7. Our slope is equal to 1/2, negative 1/2. B is equal to 7. We begin graphing at positive 7 on the y-axis, 2, 4, 6, 7. And then we're moving in the slope of negative 1/2. So we go down 1 in the y direction and to the right 2 units, down 1 and to the right 2, down 1 and to the right 2, and so on. We can graph a line through those points and see where those 2 points intersect. Okay, those 2 points intersect there, and it looks like that is at 1, 2, 3, 4 in the x direction, and 1, 2, 3, 4, 5 in the y direction. Now, our final step is to check. Let's make sure that that is a solution to the system of equations. We're going to be checking each equation when x is equal to 4 and y is equal to 5. The first equation, 3x is 3 times 4 plus 2y, which is 2 times 5, equals 22. That's 12 plus 10. That does equal 22. We know it works in the first equation. Let's try the second equation. So that's 2 times 4 plus 4 times 5. That's 8 plus 20. That does equal 28. So we know that this is a solution to that system of equations. Let's try a few more problems where we're solving systems of linear equations by graphing. Let's write first, the first equation is x equals 6. Now x equals 6 is one of those special equations. It only has an x in it. So if you remember the VUX, where V stands for a vertical line with undefined slope, and the equation only has an x in it. So we're going to locate 6 on the x-axis using a scale of 1 unit here, and we know that this is going to be a vertical line with undefined slope. Now our second equation has both an x and a y in it, so it would be nice to get that equation into the form of y equals mx plus b. we're going to take 1/6 x minus y equals 1. We're going to subtract 1 over 6x from both sides of the equation. We get negative y is equal to negative 1 over 6x plus 1. We want to multiply both sides by a negative 1, either multiply or divide both sides by a negative 1, so that we get the y by itself. Y is equal to positive 1 over 6x minus 1. This is a linear equation with a slope of 1/6 and a y-intercept of negative 1. We begin graphing this line at negative 1 on the y-axis, and then our slope is going up 1 unit and to the right 6 units. So rise over run 1 over 6, and you can also go in the other direction. We can draw those two lines, and we can see that we have an intersection point here. That intersection point is 6, 0. And we want to check that in both of the original equations. The check, well, we know the first equation was x equals 6, so that makes sense. It is a solution to the first equation. And then the second equation, 1 over 6x, which is 1 over 6 times 6 minus 0, does that equal 1? 1 over 6 times 6 is 1, and 1 minus 0 is equal to 1. So we can say that this is a solution to that system of equations. Let's try example in D. 2x plus 5y equals 32. We want to write that in y equals mx plus b form. We do that by subtracting 2x from both sides of the equation. We get 5y is equal to negative 2x plus 32. Now we're going to divide both sides by 5, and we get y equals negative 2x over 5 plus 32 over 5. So that means our slope is equal to negative 2 over 5, and then the y-intercept is 32 over 5. Which is 6.4. Okay, so we begin graphing the x-intercept the y-intercept b at 6.4. We're going to go up 6 units, 0.4, and then our slope is negative 2 over 5. This may be a little tricky because our y-intercept has decimals in it, so we're going to move down 2 units and then over 5 units. Okay, and then we can graph a line through those 2 points. Okay, if you have a ruler, this is a really good time to graph using a ruler. And let's look at the second equation. 3y equals 20 minus 2x. I'm going to rewrite this as 3y equals a negative 2x plus 20, so that we can write it in the form of y equals mx plus b. Then we divide both sides by 3, and we get y equals negative 2/3 x plus 20 over 3. So the slope here is negative 2/3, and the y-intercept is 20 over 3, which is 6.6 repeating. So we graph starting at 6.6, and then our slope is negative 2/3, negative 1, negative 2 over 3, negative 1, 2 over 3. Okay, it looks like this is going to go off the page. Take your time to graph these. Again, we're going from the 6.6 down 2 units. That's 1, 2 units, and then to the right 3 units, down 1, 2 units, to the right 3 units. We can draw a line through those points, and it looks like the intersection point, it's not really clear based on my graph, but that's why we always want to check our work. It looks like these 2 lines intersect at this point with coordinates 1, 6. It is really important that we check our solution. So if we check 1/6 with the first equation, 2 times 1 plus 5 times 6, does that equal 32? That's 30 plus 2, it does equal 32. So it is a solution to the first equation. We also want to check to make sure it's a solution to the second equation, 3 times y, or 3 times 6. Does that equal 20 minus 2 times 1? 3 times 6 is 18, and 20 minus 2 is 18, so that is a solution to the system of equations. So this example really does show you that graphing is a method, although it may not be the easiest method. So in the future sections, we're going to be looking at both the substitution and the elimination methods as alternate ways of finding solutions to systems of linear equations. In these examples, without graphing, we want to determine the number of solutions of a system. And note the systems have no solution or an infinite number of solution. So we will either end up with case 2, where the two lines are parallel and we have no solution, or we could have an infinite number of solutions. That's case 3. So recap here. In case 2, when there's no solution, we can see that the two lines are parallel. So that means the parallel lines have the same slope, but different y-intercepts. So if we could write both of these equations in y equals mx plus b form, if both of those lines have the same slope, but different y-intercepts, then we have case 2, where there's no solution. Or we could have case 3, where you have an infinite number of solutions, and we can see that that would end up with the same line. So the lines would have the same slope and the same y-intercept. Okay, so we can do part A by solving for y, find the slope and the y-intercept. We have 4x minus 16y equals 12. I'm going to subtract 4x from both sides, and I get negative 16y is equal to negative 4x plus 12. And then I'm going to divide by negative 16 on both sides. And then I get y is equal to negative 4 divided by negative 16 is a positive 1/4. And then 12 divided by a negative 16, well, that is negative 12 over 4. Negative 12 over 16, which can be reduced to negative 3/4. All right, and then the second equation is already written in the form of y equals mx plus b. So we can see that the first line, the slope is equal to 1/4, and the y-intercept is negative 3 over 4. In the second line, the slope is also equal to 1/4, and the y-intercept is negative 3/4. So we can say that in this case, they both have the same slope and the same y-intercept. So we can say that this is case 3. We have an infinite number of solutions. Because those two lines are identically the same lines, and what we're looking for is finding all of the intersection points. And there's an infinite number of intersection points, all of the points that are on that line. Let's look at part B. Taking our first equation, negative x is equal to y, we can write that as y is equal to negative x. We can see that this has a slope of negative 1 and a y-intercept of 0. The second line, x equals 6 minus y, we can write in terms of y equals mx plus b. I'm going to add y to both sides of the equation, and I get y plus x is equal to 6. I'm going to subtract x from both sides to get y is equal to negative x plus 6. Here we see that the slope is negative 1 and the y-intercept is 6. So notice that we have the slopes are the same, The slopes are both -1, but the y-intercepts are different. So we can see that these will be graphed as parallel lines, and this has no solution. This is case 2. The lines are parallel. So these two lines will never intersect because they have the same slope but different y-intercepts.